I'd like to move on now to what we could expect, not for specific examples, but more generally. I would like to consider now general scattering theory. Now that we've built up all of this good intuition, general scattering theory, and of course this is going to be in one dimension, of course. Right. So the most general type of scattering problem that I could imagine would be something as follows, right? I would have some potential, again, V of x, and I will imagine sending in some wave packet here from the left. You, of course, could imagine doing it in from the right, but I'm sure you guys are clever enough to be able to flip around the what I'm going to draw next and consider the leftward case. Right? We will just define our x-axis so we can keep generality as moving in the same, as pointing in the same direction as my incoming packet. So my packet's going to come in, and it will have some energy level E, right? With some energy E, or concentrated with momenta very close to E. And now, in scattering, what happens is we send in a particle that travels first through free space, right? And then it interacts with the interesting part of my system. And that interesting part of my system, I will say, will begin at x equals 0. And at that location, the potential then, which was 0 over here, right, in free space where I'm sending in my packet, now becomes non-zero. It could do any number of crazy things. Maybe it begins, parabolically, and then maybe it levels off, and then maybe it has a discontinuity, and another discontinuity, and yet another. Maybe it even goes above the energy, and then maybe it comes back down, right? But then at some point, and I will call that second point L, the potential again becomes I leave my system. There's no more forces acting on my particle, so that in general, with a zero force, that means a zero slope in my potential once again becomes constant past location L. And the value of that constant, of course, will be called V naught. So it's very similar to what we've done before, except now, instead of it being some kind of simple step in here, it is now going to be some complicated potential that extends out over more than just a simple discontinuity at a single point, but extends over this distance from 0 to L. And we could then go ahead and analyze this situation. I want to think in general, what kind of results can I expect in this general case? So, again, just to be organized, we will divide things into regions. There's going to be a region 1, which is my incoming region. It's classically allowed. There's then going to be a region 2, which also is a classically allowed region. We now have enough experience that we could directly write down the solution to or at least the general form of the solution to the time-dependent Schrödinger equation. That solution then would come in the following form. I will have my general case, like the very general case above. I would make it as a superposition, again, of incoming wave vectors. So in region 1, there will be a K1. And it will be the same formula, actually, because I've got 0 potential. 2m over h bar squared times E. Region 2, likewise, would have a K2, following just what we had in our last example. Again, because my potential is constant over here, so this would be E minus that same constant I've been calling V naught. I would then, I can send in any shape packet that I want. I've been pretty happy with my Gaussian packet. You can do the analysis for any shape, though it doesn't change our conclusions any. Minus sigma squared. I will peak things again around this incoming wave vector k naught. I'm then going to have my time-independent Schrödinger equation solutions, which I will put this 1 over 2 pi to make sure they are properly normalized pure states of momentum. In this first region, I will have sines and cosines, but I'm going to rearrange my solution, of course, in the same form that I've been analyzing. So I'll have this simple incoming wave, e to the I k1x, and that, of course, once again represents my psi sub in, my incoming part, right? Then I will have, and I will choose my factor, so the number in front of this one is 1. There is then going to be some kind of a reflected or backward traveling wave in that region, so there'll be a minus I k1x. And there's going to be some number in front of here. I don't know what this number is, right? To get the number that goes here, you actually have to go through all the math and do the solution like we've taught you. But it's going to be some kind of complex number multiplying this backward traveling wave. So we will call that number capital R. In general, it will be a function of K1. The product of these two things, when combined with the whole rest of the solution, will give me this backward or reflected traveling wave that I'm expecting. I will call that psi sub r. And this new coefficient I'm introducing is called the reflection amplitude or reflection coefficient. There are two different types of names that we could use. Reflection coefficient or amplitude is that r. And this is my solution, of course, for x less than 0. Now, in between, where x goes from 0 up to L, I, of course, don't know what I'm going to get. You have to solve for what's going on in all that complicated region. But we are really focused in on regions 1 and 2 because this is where ultimately, in the end, we expect there to be my final reflected packet and then my final transmitted packet coming out. And then finally, for the time-independent piece, right, I have the solution when x is greater than or equal to L. And again, it's an allowed region. So in general, I will have forward and backward traveling pieces. The wave vector here in region 2 is different in general. So that's e to the I k2, which, of course, is implicitly a function of k1. I'll just write that. That's not a multiplication. It's just reminding me that this is a function of k1 times x. We do know, though, because we have left incident boundary conditions, that there's no backward traveling piece out here. The one thing we don't know is what coefficient we will find ending up in front of this. I will call that capital T of K1, right? So this entire part, so the capital T is the transmission coefficient, or sometimes called the transmission amplitude. And this whole piece that gets constructed from that part of the solution, I will call, again, psi sub t. That will represent some transmitted packet moving out here. And the last bit that I haven't included, let's hope I can squeeze it in, there's not a whole lot of room left, is the standard time dependence that we always have, which depends on this energy here, which is simply related to K1. So there will be this overall factor of e to the minus I h bar k1 squared over 2m, I think I've got it, yes, times t. So that's the general solution that I can expect. And you can see the behaviors also that we are expecting to find. What we would expect in general then would be for a system like this that there's going to be, just like we have been saying, there's going to be before, and in the before case, of course, I've got just my incoming packet, and between 0 and L, right, there won't be anything going on during that before time. The after time, what I expect to happen is that my packet will end up, all the particles will eventually be either reflected or transmitted coming out, and again, without anything left in this in-between region. So these are the behaviors I'm expecting, and I'm asking, again, the same general questions, when and where are each of these packets, and, of course, what are the probabilities of the reflection and the probabilities of the transmission.